Hi and welcome to this course on advanced graph neural networks. As the name suggests, this is not a beginner course. I assume that you're familiar with neural network building and training. And I also assume that you're familiar with graph structures and training simple graph neural networks. If you have these prerequisites, this is the right course for you. Let's do a quick overview of what graph neural networks is all about before we dive into the content of this course. Now, graph structures are fundamental data structures in the computer science. Graphs are made up of nodes and edges. Nodes can represent entities in the real world, and edges typically represent relationship. There are different kinds of graphs used to model different kinds of real-world entities and relationships. For example, a directed graph is where the connections between the nodes have a certain directionality. Undirected graphs, such as the one that you see here on screen, the connections are bidirectional. We then have homogeneous graphs where all of the graph nodes are of the same type. Heterogeneous graphs where all of the graph nodes can be of different types, and so on and so forth. Graph structures are special because you can have feature representations of nodes and edges, and there is the structure of the graph itself, the interconnectivity between graphs. If you want to work with deep learning algorithms on graph data, well, the right thing is to use graph neural networks. These are neural network models designed to operate on graph, and they are set up in such a way that they are capable of extracting complex dependencies and interactions between nodes and edges which traditional models may not capture effectively. Graph neural networks are used for different kinds of prediction tasks. For example, you may have node-level prediction tasks which involve making inferences about individual nodes within the graph by leveraging the node's features and its connections. Identifying fraudulent accounts in a banking or transaction network by analyzing transaction patterns and relationships between accounts. Graph neural networks can be used for edge-level predictions as well. These focus on the relationships between pairs of nodes and determine the likelihood strength or type of connections between nodes. For example, in protein-protein interaction, you determine whether two proteins will interact within a biological network, crucial for understanding cellular processes and disease mechanisms, and you can have graph-level predictions as well. This involves making inferences about entire graphs or subgraphs and is used to categorize or predict properties of the entire structure. For example, molecular property prediction. You can predict the properties of a molecule such as solubility or toxicity by treating the entire molecule as a graph where the atoms are nodes and bonds are edges. So how do graph neural networks operate on graph structures? The intuition behind a GNN is borrowed from the idea behind convolutional neural networks. For each node in the graph, GNNs aggregate information from the features of the node itself as well as from nodes in the neighborhood of the target node. Convolutional neural networks extract features from images by applying a sliding window kernel over the input image. The image is treated as a grid-like structure of pixels, and this sliding window extracts information from every pixel and all of the neighboring pixels as well. This aggregation of neighborhood information allows convolutional neural networks to learn features from the underlying image. The same idea can be extended to graph neural networks as well. An image, of course, can be represented using a regular matrix. Every pixel in the image has exactly the same number of neighbors. Graph topologies are more complex and arbitrary. Graph neural networks generalize this idea of convolution, that is, aggregating information from the node and its neighbors. Beyond simple grid-like structures to arbitrary topologies, every layer of graph neural network aggregates information for each node in the graph. This information is aggregated for each target node from the neighboring nodes as well as the current node. As you might imagine, this idea of convolution when applied to graphs is much harder than when applied to images. With graphs, there is no fixed notion of locality. Every node in a graph can be connected to an arbitrary number of nodes. In an image, you aggregate information from neighboring pixels by applying a sliding window. There is no such sliding window that you can apply to graphs. Graph neural networks does set up a separate computation graph for each node in the original graph structure. The computation graph for each node is based on the local neighborhood for that node and is different for each node in the graph. So if you have 100,000 nodes in your graph, for every layer of the graph neural network, a separate computation graph will be set up for each of the 100,000 nodes. Every layer in a graph neural network generates embedding representations for every node in the graph structure. How are these node embeddings computed? Well, every layer of the graph neural network for each target node in the graph basically sets up a separate computation graph. Every node in the graph gets information from its neighbors, which it uses to update it embeddings, and those neighbors then get information from their neighbors. This information that is asked from the local neighboring nodes is transformed using a learnable weight matrix and then propagated to the target node. With this basic overview, let's quickly discuss the topics covered in this course. We'll first perform node classification using graph attention networks, which leverage attention mechanisms to assign different weights to neighboring nodes, allowing for more expressive and accurate node representations in classification tasks. In the next topic, we'll perform graph classification with and without neighborhood normalization. Neighborhood normalization adjusts the influence of each node's neighbors based on their degrees, leading to more balanced and effective aggregation of features across nodes. However, applying neighbor normalization can decrease the expressivity of GNNs in distinguishing certain graph structures, and it may be possible to improve the performance of graph classification by eliminating neighborhood normalization and using skip connections. And finally, the last topic, we focus on link prediction using graph autoencoders. Graph auto low-dimensional embeddings of nodes, and use these embeddings to predict the existence of edges by reconstructing the adjacency matrix.